Got it? Okay, let's begin with a prayer. Dear Heavenly Father, we thank you again for this opportunity we have just to meet together and study calculus. Just pray that you'd help us to use this time wisely and that we would glorify you in what we do, Lord. In your name I pray. Amen. So, sorry. The jerk who was in here before forgot to erase the board. So, we're still in chapter 11. And, part of the thing that's been weirding me out is I keep remembering these problems that were difficult, and I haven't really found them in chapter 11 yet. And I think what I'm remembering is various chapter 11 questions which come up in chapter 12. So, I think I might take a few minutes today to look at one of those, just to kind of give you an example of something that's a little bit less easy, but get us started on the path of thinking some of the deep thoughts we ought to be thinking. Of course, I'm going to spend a good bit of today on L'Hopital's rule, but there's a few other things I should take care of today while we're at it. Excuse me. First of all, I need to state a theorem for you guys. This is Theorem 11.3.6, something I forgot to cover, but I should. It's an important one. Here it is. An increasing sequence. I'm changing the terminology. Which is bounded above. All right. Converges to the least upper bound of its range. Let me be a little bit more symbolic about that. All right. So what we're saying is we've got a sequence, right? A sub n with a sub n plus 1 greater than or equal to a sub n. And there exists some m, right, such that a sub n is less than or equal to m. And these things are true for what? For n equals to 1, 2, 3, and so forth, forever and ever and ever. So in other words, we have a sequence, it's increasing, it's bounded above, right? That a conclusion is that the limit, punchline, then limit as n goes to infinity of a sub n, all right, is equal to the least upper bound of the range of n. So the range of a sub n is just a1, a2, a3, and so forth and so on, forever and ever. It's that infinite set. It's the least upper bound of that infinite set. So that's one part of the theorem. The other part of the theorem is the same thing for decreasing. If you have a sub n plus 1 less than or equal to a sub n for all n in the natural numbers, and if you have that a sub n is less than or equal to m for some real number m, and all n in the natural numbers. So in other words, we have a decreasing sequence which is bounded below, backward, sorry, I got that wrong. Oh yeah, I just did that one. I'm an idiot. The other way, m less than or equal to, it's a lower bound. Okay, lower bound. It's a lower bound on the range. All right. Oh, fun. That. Ay, ay, ay. The limit, as n goes to infinity, of a sub n is equal to the greatest lower bound of the range. Right. I think these are usually called the bounded monotonic sequence theorems, or theorem. It says a bounded monotonic sequence converges. And not just that, it converges to either the least upper bound or the greatest lower bound of the range as appropriate. The proof is on page 541 of your text, and it's basically based on using the least upper bound property of the real numbers. I'm trying to think of a good example for this one. Here, I'll use his example 4. Excuse me. So here's an example he gives. These are pretty nice theorems, right? Because all you got to do is show that your sequence is increasing or decreasing, right? And then it's bounded above or below as appropriate, and that gives you convergence. That's kind of hands-off, right? It's not as sort of direct, algebraic, manipulative as, say, L'Hopital's rule. Although L'Hopital's rule, of course, is very, very wonderful and beautiful when it works. But this is also a nice tool set to have. So suppose you have a sub n is equal to 3 to the n plus, oh, I'm sorry, bad font choice, parentheses, 3 to the n plus 4 to the n to the 1 over n power. Now, I guess I can solve this by L'Hopital's rule. I'll tell you what, I'll take a stab at this with L'Hopital's rule here in a few minutes, but let's see how the bounded monotonic sequence theorem does it for us. So his point is this. Golly. 3 is equal to, oh, very sneaky, 3 to the n to the 1 over n. Aha! Aha! That one, you get that one? And this is clearly less than 3 to the n plus 4 to the n to the 1 over n. I think that's reasonable, right? If you look at the function f of x equal 3 to the x, then f prime of x is log 3 times 3 to the x, right? That's greater than 0 for x greater than 1. Well, it's actually always greater than 0. The point is, that's an increasing... Oh, that's not what I want. I want the 1 over n. I'm an idiot. Oh, let me shut up. I don't want to prove this. I mean, I guess I could, but I'm distracting us. This is not the level of proof that you're held. I mean, this is a reasonable step for us, right? Do you see why this is a reasonable step? I'm taking the 1 over n of something, right? Something to the 1 over n is an increasing function, right? If I take 2 to the 1 over n versus 3 to the 1 over n versus 4 to the 1 over n, 3 is bigger than 2 to the 1 over n, 4 to the 1 over n is bigger than 3 to... It's right, it's an increasing function. Do you agree? Do I need to prove that, or I think it's fairly clear. So, but we could prove it if we wanted to. So I'm taking this and making it bigger, right? So this quantity is larger, right? In contrast, if I had 1 over 3 to the n, it is not less than 1 over 3 to the n plus 4 to the n, right? I couldn't do that because the reciprocal function is not increasing, right? For a counterexample, when you can't do this, all right? So the inequality goes the other way there. All right, getting to the point. What does he do next? Oh, very sneaky. This is greater than 4 to the n plus 4 to the n to the 1 over n, right? So he's trading the 3 to the n for a 4 to the n. Seems legit. And that's what? That's 2 times 4 to the n to the 1 over n, right? And of course, by laws of exponents, this is equal to 2 to the 1 over n times 4, right? All right, I feel like at this point I've been trying to avoid the explicit analysis of the 1 over n function, but let me just go ahead and hack away at it for a second. If we let f of x equals to 2 to the 1 over x, right? What's the how do you do this derivative? Let's see, so we do what? Log of 2 times 2 to the 1 over x, right? Times the derivative with respect to x of 1 over x. Chain rule. And so what is that? Minus log 2, 2 to the 1 over x over x squared. So what does that say about 2 to the 1 over x? Oh, yeah, sorry, I'm an idiot. I keep thinking about this over here, but that's a different function. So let me stop that. Okay, so this is less than 0. Very good, right? So what's that say? That says that 2 to the 1 over x is greater than x1 is greater than 2 over 1 over x2 if x1 is less than x2, right? It's decreasing. So if you apply this, so take x1 and x2 to be any pair of integers, you can see you have 2 to the 1 over 2 to the 1 over n1 is greater than 2 to the 1 over n2, where n1 and n2 are integers, right? And so, of course, what's the small? I mean, this is at, what's at the bottom? Well, 2 to the 1, right? So like this is an upper bound on this. This is like I was talking about last time. If we have a decreasing sequence, like this is a decreasing sequence, right? 2 to the 1 over n is a decreasing sequence. So an upper bound is just the initial element in the sequence, which is what? Just 2 to the 1, right? So this is, I'm going the other way, sorry. This is less than 2. That's the largest this can be is 2, right? 2 times 4. Oh, we haven't shown anything about, all we've shown at the moment, right? We have shown that an is bounded, right? So a sub n, this is a sub n, right? And this shows that a sub n is bounded above by 8, right? And I would argue it's also clear that a sub n is what? A sub n plus 1 is greater than or equal to a sub n, right? Let me skip the details if you don't mind. I think he has the details in here, but well, yeah, he actually does have the details right there. So he shows explicitly through inequality arguments that it's increasing, all right? So what's that say? So we have an increasing sequence that's bounded above, therefore what? Right, so the limit as n goes to infinity of 3 to the n plus 4 to the n to 1 over n is equal to the least upper bound of this set. Now, if you don't mind, I'm going to be lazy and not calculate the least upper bound directly because it seems like a pain to me at the moment. Yep. I'm sorry, I couldn't hear you over the trash can rolling in the hallway.
That is a decreasing sequence, not a
Oh, is it decreasing?
I
This is decreasing sequence? Let me think about this. Huh. No, this step is still legitimate, but that's a separate question. I'm an idiot. Let's see here. So you plug in 1, you get 7. You plug in 2, what do you get? 9 plus 16. Yeah, 5, 7, 5. Yep, decreasing. Oh, you're right. So how does that change things here? If I would... Actually, I should have finished the example to the end rather than trying to skip details. See what happens when you try to skip details. So it's decreasing, right? Which means that it converges not to the least upper bound, but to the greatest lower bound. And guess what? This thing is bounded above and below. So what we should have said is that 3 is... The relevant bound is that one, right? So it's bounded below by 3. And it's decreasing, so thank you. That is very helpful. Let's see how to calculate this thing directly using L'Hopital's rule. So we're trying to, and I'm going to, related limit. Let's look at it in terms of x. So we've got 3 to the x plus 4 to the x to the 1 over x power. I'm going to take the limit as x goes to infinity. All right? Question is, what's this limit? So here's what we do. We take the exponential of the natural log of this limit. I should really have given this expression some kind of name. It's getting tiring to keep writing it, but I will keep writing it. That's why they pay me the big bucks. Let's see here. Not really. Let's see here. They pay me enough. Okay, so why can I do that? Well, to be honest, I mean, we know that the limit exists by our previous work. I suppose one thing, but anyway, so this is in some sense taking out a logical low, and I'm assuming that the limit's positive, right? If we work this out and we find out that this limit is -7 or something, then we need to search we need to go back to here and say, that was nonsense. We can't do that, right? So you have to do something else. But supposing that after we keep working, we get to something positive or infinite, right? Or 0 in a certain sense, we can understand it, right? If this works out to 0, that means the whole limit's going to like minus infinity. I'll shut up. That's not what I mean to say. Anyway, let me shut up about the... So this is an identity, right? The exponential of the log of something is just the something again. And then what we do is we bring the limit outside using the continuity of the logarithm. So this is the limit as x goes to infinity, right, of the natural log of 3 to the x plus 4 to the x to the 1 over x. You guys with me still? Okay? No? I can't calculate this limit directly. It's an indeterminate type. This is type infinity to the 0, indeterminate power. Okay, so we're stuck. We got to do something else. So this is a standard trick. This is going to work for us for every problem, what I'm doing right now. So then the next step is this is exponential of the limit as x goes to infinity of 1 over x times the natural log of 3 to the x plus 4 to the x. Now we've got something, all right? So what I usually do at this point is I give this thing a name and I work on that, and then I come back once I've figured that out, and I plug it back into here as appropriate. So I call this thing star. This is my typical move. I made it famous. Let's see here, star. The standards for comedy are low today. That's what I like to hear. Limit as x goes to infinity of, check it out, yo, you got log of 3x plus 4 to the x divided by x. Hey, that looks like a job for Mr. L'Hopital. Yes, because we have infinity upstairs, we got infinity downstairs in the limit, right? Let's type infinity over infinity. We can use L'Hopital's rule. Well, that presupposes we know how to differentiate. But you guys can differentiate, right? Let's be optimists. You can differentiate. Kind of a mess. But upstairs I had to do the chain rule. So it's 1 over 3 to the x plus 4 to the x times the derivative of 3 to the x plus 4 to the x. The derivative of 3 to the x plus 4 to the x is log 3 times 3 to the x plus log 4 times 4 to the x. Right? Well, it is. Derivative of x, on the other hand, is 1. That was less exciting. And let me clean this up a little bit before I get too carried away here. Limit as x goes to infinity of what we got. We got log 3 times 3 to the x plus the log of 4 times 4 to the x divided by 3 to the x plus, oh man. So that happened. So now it's infinity over infinity again, right? So we can do it one more time. L'Hopital's infinity over infinity. Why didn't I say extending n to be continuous? Because it's a function of x. Very good. Okay, that was an easy question. Thank you. All right, so log 3 squared, 3 to the x, plus log 4, quantity squared. Oh, man. I don't think this is going to go anywhere, guys. So sometimes you got to do something like this because you got to realize, you know, some paths are not wise to go down. Now, it's not dumb to do this. It's dumb to do it again after you've done this. Right? The first time I'll allow. If we kept doing it, then I would feel like, oh man, we need to think about our life. So some other technique needs to be used here to take care of this limit. Any ideas? I'd hate to admit that this example has to be handled by the bounded monotonic sequence theorem. So I would like to say that we can L'Hopital pretty much everything, but this is making me wonder. We can do algebra though, right? So algebra, our old friend. I look at this and it seems to me maybe if I divide by 4, everything by 4 to the x, I'll get something reasonable. So like this is log 3 times, what's 3 to the x over 4 to the x? Three-fourths to the x, right? So this is log 3 times 0.75 to the x power. If you'll allow me some decimals. You guys are engineers for the most part. You like decimals, right? You're like, yes, decimals. Much better. 0.75, my precious. See here, plus 1. Sorry, I'll stop bringing Gollum into this. Anyway, so yeah, oh yay! 0.75 to the x does what? This is one of those things that I should have proved for you in section 11.3, but was too lazy to bother. Or was it 11.4? It was 11.4. One of the things in 11. Well, I don't know. Anyway, just common sense. This is a number of magnitude less than 1. What happens to this as x goes to infinity? This piece goes to 0. This piece goes to 0. And that's good news because we're left with 0 plus the natural log of 4 divided by 0 plus 1, aka log 4. So turns out L'Hopital's rule can't do everything. sometimes we still have to know algebra. Sorry, guys. I can't fix that for you. Oh, and that's not the answer, is it? This is just what? This is the star. So now I go and I stick it back up in here. And what's it give me? Exponential of the natural log of 4, which is otherwise known as 4. Woohoo! So we calculated the limit to be 4 using L'Hopital's rule and a little bit of algebra. On page 541 to 542, he shows that the limit is 4, I think. Does he? I think he argues that 4 is the... trying to decide whether he's made this claim or not here. Oh, exercise 43. He just made it an exercise. So like number 43 in this section is to find the greatest upper bound of the example 4. Greatest upper bound? Greatest lower bound. Which apparently is 4. Hey, here's a more fun way to look at this. By doing this calculation with L'Hopital's rule, right? By doing this L'Hopital's calculation over here, you know that if I replace this x with an n, the sequence as n goes to infinity also has limit 4, right? The bounded monotonic sequence theorem is true. So this gives us an indirect way of calculating that the greatest lower bound of this monstrosity is 4. That's pretty cool, right? Because we calculated 7, we calculated 5, and if you kept going, you probably get closer and closer to 4, but we don't have to. We know from this calculation and logic that this works out to 4 without direct calculation of it, which is kind of cool. Yeah.
Can you explain this step really quick?
Absolutely. This is limit laws. Oh, this one?
Yes.
I divided the top and the bottom by 4 to the x. So divide the top by 4 to the x, divide the bottom by 4 to the x. Which is allowed. Of course, this, it was. I mean, it's not wrong, but it's not wrong, but it's not right either. Right? I mean, it's just not helpful. Okay. You guys have questions about homework before I continue with my jibber jabbering? Jibber jabber jibber jabber. I think I've told you all of the most exciting features of Chapter 11. Modulo... I mean, we still have a few indeterminate powers to go, which I'll keep picking away at those until we understand them. The one remaining topic in Chapter 11, which is huge, is section 11.7. That's an important one. Improper integrals are one of the bigger things you'll learn in this course that are important for applications. But we'll get to that Tuesday. I guess I still owe you guys what? Actually, could we move the quiz to like Tuesday this week?
Yeah.
Okay. Yeah, I think I'd like to do that. Because Monday I'd like to talk about improper integrals. And I'd like to ask a token improper integral or two on your quiz. So, all right. Do remind me to post the solutions to your homework, right? So that you have something to look at. I mean, you have all the odd problems in the book already, of course, but I do want you to have a little bit more than that. All right, so let's get back to L'Hopital's rule. So let's see here, another standard example. Indeterminate powers. Let's work out probably the most important example. This one was what? We already did infinity to the 0 here, right? Finally. Ah! Example. Limit. N goes to infinity. 1 plus 1 over n to the n power. All right. It's a pretty standard example, but let's go through it. So what we're going to do is we're going to rewrite this as the exponential of the limit as n goes to infinity of n times the natural log of 1 plus 1 over n. That's a very Machiavellian calculation I just did. I did all my evil all at once. So I first inserted the exponential log. I then pulled the limit inside the log, outside the log, using continuity of the logarithm. And then I used the properties of the logarithm to pull down the power. I did all of that in that one step. Is that okay? Well, I hope it's okay. You're like, can we do all three of those steps in the same step on our test? Yes. Yes, you can. Let's see here. It's always the same three steps for all of these problems, okay? You bring the limit outside. First of all, you insert the exponential log identity. You pull the limit out of the log and you use the power property. What does the power property do? You got log of a to the p. It becomes p log a, right? The point is, if this was 0 to the 0, or 1 to the infinity, or infinity to the 0, when you use this log property, it becomes 0 log 0, or 1 times the log of infinity. I don't know. I shouldn't do it that way. My point is, let me not say it this way. I'm not being careful enough. The point is, when you use the property of the log, not being precise enough. If you use the property of the logarithm here, it will convert the indeterminate power to an indeterminate product, and also it involves the logarithm. All right? So that happened here. See? We go from having 1 to the infinity to having something like infinity times the log of, what does this do? 1 over n goes to what? 0. So this is log of 1, which is, so this is like infinity times 0. See? It's an indeterminate type, but not of the power kind, of the product kind. And then, so usual name calling, call this thing star. All right? So star is the limit as n goes to infinity. If you were lazier than me, you might avoid writing it again. But I'll just write it again for the sake of being clear. Oh, actually, I'm going to be slightly unlazy. This is the natural log of 1. I'll be slightly lazier. I can rewrite star as what? 1 over 1 over n? Do you agree? Do you disagree? What did I do? I used a often underappreciated identity. N is equal to 1 divided by 1 over n. So like 8 is 1 divided by 1/8. Right? You have a piece of pizza pie with 8 pieces. You get 8 slices. Anyway, okay, I shut up. Now this, so now we have, what, 0 over 0. So L'Hopital's type 0 over 0. Ah, man, I guess I need to be, here we go again, extending n continuously. You're like, you're writing too much. All right, fine. Man, you guys are lazy. All right, let's see here. I approve. Let's see here, limit, mostly. N goes to infinity. Ooh, I like the smirker. So the derivative of the top is 1 over 1 plus 1 over n, right, times the derivative of the argument of the logarithm, which is just what? Minus 1 over n squared. And then downstairs, derivative 1 over n minus 1 over n squared. Well, isn't that convenient? So a little bit of algebra here. I have a limit as n goes to infinity of 1 over 1 plus 1 over n, which is equal to what? So we can actually, so that this goes to 0, right? So by limit laws, we get 1. Therefore, this up here is equal to exponential of 1. Or, if you prefer, the limit as n goes to infinity of 1 plus 1 over n to the n power is equal to e. Some people like to use this as the definition of e. Okay. Any questions? So it looks like we worked out 1 to the infinity. It wasn't 1. This time it turned out to be e. You can make it turn out to be any positive quantity you like. Let me show you how. A little bit of color coding. I'll use red. What happens if we stick an x right here? Where does that go to? It goes here, right? Then where does it go to? Becomes part of the star. So it's here, right? But you can pull it out. Because x has no dependence on n, so it pulls out of the limit. Like that. And then it's here. And then instead of getting 1, we get x times 1. But a civilized human being would write that as x. So, in short, the limit of 1 plus 1 over n to the nx power is equal to e to the x. So here we have a limit of type 1 to the infinity, and you can obtain anything that you can obtain as e to the x. In other words, any positive number you can hit with a limit of the form 1 to the infinity by this simple calculation. Right? It's pretty cool, I think. This formula appears if you study compounding interest, right? Like if you do simple compounding, you get formulas like this. And then you keep multiplying it and multiplying it and multiplying it and multiplying it, right? But then the power, like the rate, you divide by the number of compounding periods. And if you take the limit as that goes to like a continuous compounding, you get this thing. There's another way you can understand it. Don't ask me to explain that. I don't care about money. All right. What are we to? We need other examples, yeah? Ooh, look at this one. The limit as x goes to 0, 1 over sine x minus 1 over x. Sorry, I got bored of powers. Now we're back to other things. I guess I still owe you a... I guess I don't. I mean, if you understand these two examples, I've gone pretty slow. I think you could do any of these. It's always the same thing. You just insert exponential log, use the power property, and then you do ordinary L'Hopital stuff. To the star. This one, though, is probably something I should talk about. We haven't done anything quite like this. How do you do this? What's the problem here? Yeah, sine of x is super tiny, close to 0, right? And so is x. So we've got 1 over something very, very small minus 1 over something very, very small. Yes, in fact, this is infinity minus infinity, right? Which is not 0. It's an indeterminate form, right? So this is type infinity minus infinity. How do you resolve this? We can't L'Hopital this thing. It's not in the right format. What'd you say?
So isn't there a rule? There's a rule.
Well, yeah, I mean, if we were physicists, we'd do an experiment, put a label on it, sweep the infinity under the rug, come up with a name for it, call it renormalization or something, and then we'd be good to go. Get a Nobel Prize. I like doing good stuff, but since we're not physicists, we got to work it out. Sorry, just a little renormalization humor there for you. Guess don't know about the bare masses. No. All right, that's fine. It's okay. So I would suggest ignoring my silly references to physics we don't offer. Limit as x goes to 0. Well, if I want to make this into a fraction, because that's where my tool set is, right? L'Hopital's rule is all about fractions. Yeah, cross multiply, right? Make a common denominator. Seems like a good option here, right? So this is x minus the sine of x over x sine x, right? Aha! Now, we got 0 over 0. It's our happy place, right? I mean, we're not done, but we know what to do. Now we can L'Hopital this thing, right? Yeah, I'm sorry. I hate to give a quiz on what we've covered this week because we really haven't gotten to anything except for L'Hopital's rule. I'd like to have you have a little bit more to chew on for the quiz. So I think if I cover improper integration Monday, that will help give you a little bit, something a little bit more substantial for the quiz. Okay, so this is 1 minus cosine x. And also you can ask me questions about L'Hopital's rule problems Monday. You guys got questions now, you can interrupt me. This is sine x plus x cosine x. I'm about to cough. Oh, it's still 0 over 0, isn't it? But if we L'Hopital again, see why it's so important in calculus to know values of like sine of 0 and cosine of 0? If you have to pick up a calculator to figure that out, you are wasting precious time, right? Just the more you know, you know? Let's see here. So that is sine x. Cosine x, product rule, plus cosine x minus x sine x. Now I've got 0 upstairs, but what do I got downstairs? Woohoo! Now we have a function which is continuous at the limit point. I can plug in 0 into this meaningfully. I get 2 times the cosine of 0 minus 0 times sine of 0, which is fine, right? This is not indeterminate. This is just 0 over 2, also known as 0. So this limit works out to 0. Don't get the wrong idea, though. Infinity minus infinity is not always 0. Just a quirk of this example. Just like 1 to the infinity is not always 1, it could be anything, any positive quantity you like. Right? For this example.
We can subtract infinity from
Apparently not. Let's see here. Any questions about... Listen, I will take more questions about L'Hopital's rule Monday. Let me just take the last 5 minutes of class to introduce you to the idea of an improper integral. I'll do the simplest kind. If we calculate the integral, say, from a to infinity of f of x dx, what this is defined to be is very simple. It is simply the most natural thing you could think of. It is, you just take the upper bound, you make it a variable, right? And you let that variable go to infinity. And that's how we define it. Just like that. Okay? So this is like, you know, there's a few other cases. We got to talk about going to minus infinity. We got to talk about ones that go to minus infinity to infinity. There's more stuff to say. But this is the heart of it, okay? For limits at infinity. So for example, if I was to calculate the integral from, say, 0 to infinity of x e to the minus x dx. All right? What I'd have to do then is take the limit as t goes to infinity of the integral from 0 to t of x e to the minus x dx. Now, in this kind of problem, what I like to do is I like to figure out the antiderivative off to the side and then use it. right? So like integral of x e to the minus x dx, I like that to be my dv, I let that be my u. I get minus x e to the minus x plus the integral of e to the minus x dx by integration by parts. So I get minus x e to the minus x minus e to the minus x plus a constant for my antiderivative. Sorry, I took off the gloves. Limit. I'm just integrating by parts, folks. You can do it. Now, that's an antiderivative for this integrand, right? I have to use fundamental theorem of calculus part 2 to actually evaluate from 0 to t. So the t is easy enough. That's like, minus t e to the minus t minus e to the minus t, right? That's what I get from, let me call this thing, for the sake of discussion, big F of x, right? So I should be looking here by the fundamental theorem of calculus. What should I be looking at? This should be like f of t, right? Minus f of 0. Do you guys agree or disagree? Did I make a sign mistake or anything? Or is copacetic? Okay. How about when you plug in 0? Anything there? Minus f of 0. Yeah, just 1, right? So plus 1. So we got to take this limit. Some of these things are easy. So if the limits I'm writing exist, this step is legit. That remains to be seen. Let me just go ahead and rewrite this as minus t over e to the t for the first term. And then I have minus the limit as t goes to infinity, e to the minus t. And since I love to write limits, I'll write another one. Limit as t goes to infinity of 1. Just to emphasize conceptually what's going on. This guy, right, by L'Hopital's rule on just this piece, right, this piece right here. L'Hopital's rule on that piece, what do I get? Minus 1 over e to the t, right? See, if I have t over e to the t, I apply L'Hopital's rule. Derivative of t is 1. Derivative of e to the t, e to the t. So, in a street fight between an exponential and a polynomial, you should always pick the exponential. It's going to win. So, exponential being downstairs, it wins. It drives this limit to 0. This, of course, is also 0. Because e to the minus t is like 1 over e to the t. As t goes to infinity, it's 1 over a very large number. However you want to look at it, that's a basic limit. It's 0. What's the limit of 1? 1. Okay, right. So, in short, the answer is 1. Which is really interesting, right? Because what that means, guys, is that this x e to the minus x, which is what? I don't know, I forget what it looks like exactly, but it starts at 0, and it comes back to 0. So it's going to be something like this, roughly speaking. I'm not sure exactly where it's got the hump, but this is y equals x e to the minus x, right? And what this says, this calculation we just did, it says that the area under this, which has infinite length, but finite height, somehow works out to be a constant, and the area under that curve is 1. Even though one of the sides involved is infinitely long. The height also becomes infinitely small as you approach that asymptote, right? So anyway, these are the kinds of calculations we'll do Monday, all right? And also, we also do stuff like this. In fact, I accidentally gave you one of these on the test a little bit ago. Like this. This is no bueno. You guys, that's not cool. See, because that's got division by 0 at 0. Not continuous on the closed interval from 0 to 1. I accidentally put one of these on like test 1, I think. Hey, or quiz 1. One of the things I did. If you read my solution, I talk about it. The point is, we'll also be able to do these carefully Monday. But anyway, I'll shut up now. Sorry, I went over. Again, if you guys got questions, you got to interrupt me. I welcome your interruptions.